just in time.
She's good though, I like her.
Random person calling. We're very lucky tonight to have Dr. Chris Gabler speak to us. He's been to our last class. Very interesting topic. He's a plant community ecologist whose research focuses on climate change, sustainable agriculture, ecological restoration, and invasive species, especially in coastal systems. His BS in biology and pre-med are from Loyola University, and his PhD in ecology and evolutionary biology is from Rice University. So, welcome, Dr. Gabler. And I've already told him what to do if the colors on the computer turn weird. So if he keeps
to the change.
if he keeps like bending down, he's fixing it himself.
I'm definitely a walker, so I might have to be constantly running back and forth. Could we turn off some of the lights?
Yes.
That's perfect.
How's that?
That's great. All right, thank you very much. I have been working with Texas Master Naturalist for a long time. Galveston Bay chapter and the Houston chapter. I don't know if it's actually called the Houston chapter, but I'm a Houston native, and from my time at Rice, I got to start working with this group, and I'm really always happy to come and talk. It's a great group. Several of my students, a couple of whom are going to show up in this talk, are actually Texas Master Naturalists here in the River Valley chapter. So I'm going to give this. I've given this talk before. It's updated a little bit in the last couple of months from when I gave it last fall. But mainly I'm going to be talking to you about wetland ecology, and I want to tell you about sea level rise. But not just that, because we need to address that first. What I really want to emphasize are the effects that climate change in general is having on coastal wetlands. And sea level rise is typically what gets the most press and the most play, and for obvious reasons that I'm going to go over kind of briefly. But something we can't lose sight of are just the changes just what the changes in temperature and rainfall are going to do for these systems. And that's really what I want to spend most of my time talking to you about today. I'll get started by talking about some of my collaborators. A lot of this work, at least in the first half, came from my time doing a postdoc with the U.S. Geologic Survey. So this was an ambitious project I did with a great team of folks. This is Mike Oslin right there, James Grace, Camille Stagg, and the rest of the team. This was from the, at the time it was the National Wetlands Research Center, now it's the Wetland Aquatic Center in Lafayette, Louisiana. And so we had funding for this project and some of the other work from DOI, obviously, because that's USGS is under that umbrella. And we had a grant from the Federal Climate Science Center for the South Central region. And since I started at UTRGV in 2016, they've helped fund this project, as well as the follow-up projects to come from the first part of what I'm going to show you, and several other funding agencies, the Gulf Coast Plains and Ozarks, LCC, and the University of Houston, which I was soft money postdoc there after I finished with USGS. So currently, what we're working on now, sort of follow-up to that big USGS work, still involving the USGS, especially Mike and James, but largely we got a sea grant to sort of do some experimental tests on the things I'm going to talk to you about. This has mainly been done at UTRGV with my lab. Sam Ortiz and Jenny Baez are two Texas Master Naturalists. Some of you might know them, as well as some of my other grad students, Ivy Drew, Jim Ituan, who's a student from Nigeria, Paula, and a lot of undergraduates, and we even have high school students come in and work in our group during our High Scholars program, where students come in and do internships over the summer with College of Sciences. So if you know any folks at that age group or high school students that might be interested in doing that, let them know about this program, please. It's a really, really good program for everybody who's involved. The main collaborators here are Lee Smee, who is at TAMU CC and now is at Dolphin Island Sea Lab, and as well as Mike and Jim, Steve Pennington at U of H. So that's the sort of credit where credit is due. And I'll start with the elephant in the room regarding climate change impacts on coastal wetlands, which is sea level rise. And this is a very well-studied thing in a lot of different ways that I'll talk about. And it's the most intuitive. The immediate effects of sea level rise on these coastal systems is the most easy to conceptualize. So to talk a little bit about sea level rise at a somewhat technical level, right? I don't need to water it down. This group understands that when we talk about this and we try and predict what's going to happen to sea level rise, we do this through different modeling efforts. And there's variability in these models. And this data is from 2013. It's kind of cut off here. This is the 5th the fifth intergovernmental panel assessment of climate change, the IPCC, you've probably heard of. And there have been a lot of studies since then. They're coming out every time a journal on this subject or any related subject is released. We will have adjustments to estimates and refined estimates for particular areas. And so it really pays to kind of look at efforts to bring it all together, look for big patterns, big trends. And that's what the IPCC does, and they do it about every 5 years. The sixth assessment report is coming out very soon. But what this does, it brings in all the data, all the studies, surveys, literally tens of thousands of papers on this topic, and they come up with these consensus predictions. And so this is from the fourth assessment report, and these four are from the fifth assessment report. And what these are estimates of range of how much sea level rise we're going to get. Okay, from and I'll say at the bottom here, these different numbers are different scenarios, right? So they have to do, RCP stands for representative concentration pathway, and this has to do with how much CO2 and other greenhouse gases we expect are going to show up in the atmosphere. So these numbers then correspond to actual quantitative measurements of these greenhouse gases. Fewer is better, more is worse, stronger greenhouse effect going forward. And they study this range of scenarios because we're not really sure what's going to happen. Whether a country goes into a greener, more sustainable energy source, and whether, for example, more countries buy into Paris Accords, whether we meet our Kyoto Protocol targets, all those sorts of things have everything to do with whether we end up, where we end up in this span of greenhouse gas concentrations. This one, the old one, A1B, was the sort of optimistic business as usual scenario, which you might have heard people say business as usual. And this has the idea that the world's not going to totally transform, but countries are going to take this seriously, and they're going to take actions to curb their emissions and cap them, and we aren't going to continue to increase the rate we add greenhouse gases to the atmosphere. So that's an important thing to say. Not increase the rate, but that doesn't mean we're going to stop emitting greenhouse gases. And in this scenario, it's not super peachy. I'll point out that this one, RCP 2.6, is what it is now. Okay? And these are projections for the end of the century, 2080 to 2100. So why would we look at this? Why would, if we emit no more carbon, like we stopped burning fossil fuels today, why would we still have so much sea level rise? That's the remnant effects of all the greenhouse gases we've already put in the atmosphere. So those effects will continue to be felt for centuries to come, even if we don't put another milligram of carbon into our atmosphere. 4.5 and 6.0 are this one is a pretty optimistic bet on how many countries are going to reduce their emissions. This one's a little bit less optimistic, but it takes into account things like countries not all following the sort of Western model. So this one has an optimistic approach to places like China and India developing renewable energy instead of just using all the fossil fuels they can. And then 8.5 is the sort of business as usual, we don't do too much transformative work. So these are ranges, and there are lots of different things when we talk about sea level rise and climate change contribute to actually raising the sea level. So these different colored crosses down here, the horizontal bar is the median, or sorry, the average prediction, and these vertical bars are the error bars on that prediction. So some sea level is going to rise just because water is going to warm up, thermal expansion. Warmer water takes more space. You do that across the world's oceans, and a few degrees rise in temperature means centimeters of sea level rise across the world. Glaciers melting, ice sheet melting, the Greenland ice sheet, the Antarctic ice sheet melting, changes in water storage on land, and then there's some dynamics associated with those big ice sheets. So each of these things is modeled individually and taken into account for these base predictions. And long story, shorter than it could be, here are what we're sort of expecting. So this is the sort of maximum range. That's the upper limit as to what the worst case scenario might be, at least based on these models. But this is your sort of median. And I have to say that these are the two scenarios, or somewhere in between, that are more likely to unfold, hopefully. This is still a relatively optimistic scenario. And so we're talking somewhere in the neighborhood of 45 or 50 centimeters of sea level rise, about 1.5 feet by the end of the century. That's not very long. I hope my children are alive to see that. It'd be cool if I can, but that's unlikely. Maybe not so cool to see it. And to put it in perspective, this is a scaled average human height. And we may think, well, if water's up to our thighs, that's too bad. But keep in mind, that's why I put this picture of this dachshund down here, how much those changes could impact nature, smaller things that may not be able to flee from rising waters. So these are the longer term projections. This is looking 3, 4, 5 centuries into the future. Here is the low emission scenario. And again, we have a series of different ranges based on, pay mostly attention to these red bars, because that's the sum. This is looking at the same changes in ice and water. So by 2500, we are looking at over a meter of sea level rise, maybe about 60 centimeters. And this is the best case scenario. This is if we really, really curb our current emission rates. If we are in the sort of middle of path scenarios, we could easily reach over 2 meters of sea level rise. And if we get into those higher scenarios, that we could approach 6 or 7 meters. That's a lot. That's a lot. That's more than, well, it's sort of as much rise as we've had since the last ice age, essentially. It's a big deal. And I will say, these may seem like far off times, but we really need to think about generations past our own and those that we can realistically conceive of if we want to take this seriously. So let's visualize what this actually looks like. So we can kind of get in our mind's eye how much 60 centimeters of sea level rise might be. So 60 centimeters is 1.5 feet. And 1 meter, 3 foot increase is very much in the realm of possibilities, okay? It's still debatable exactly how realistic or likely that could be, but it's absolutely within the realm of possibilities. So I encourage you to try going to this website, coast.noaa.gov/SLR, and they have this cool modeling mapping feature where you can look at this. This is Galveston Bay, and this is with 3 feet of sea level rise shown. Lots of people know Galveston Bay, but let's look closer to home. Here we are in the lower Laguna Madre, and here's the Brownsville Ship Channel. This is a 3 foot increase, and those light blue highlights are areas that have been flooded. Former land that would then be underwater in the case of about 1 meter of sea level rise. Again, this is not the sort of central prediction for the end of the century, but it's well within the range of possibilities of the next 200 years. If we look at a 2 meter rise, we see a lot more than just these current low-lying areas getting submerged. A lot more are, and a lot of inland lakes become tidal. And obviously, that would come with tremendous changes across the board if something goes from fresh to a brackish to a saline system. Here's Port Isabel. 3 feet of sea level rise. We mostly just lose fringing wetlands. Parts of these canal neighborhoods are in danger. And if we look at 6, a much more dire view. Okay? You may be able to guess where I'm going next. Here we have South Padre Island, 3 feet, and we have Padre Island Boulevard underwater, and 6 feet, pretty much just the built-up hotels and things on what's not got water in the basement, or I say basement, not like a native Texan who has a basement in Texas, on the first floor. So sea level, I mean, this is eustatic sea level rise. This is just tide. This is just ambient sea level. And for any of you who have lived in coastal places before and never experienced a hurricane, most of the time we really feel these rises in sea level are during storm events, right? So if you think about where the last big storm was, and if that storm reached 60 centimeters higher, who that would affect, even in cities far inland. Think of places like Houston and how much of the city floods. Well, if sea levels were 60 centimeters higher, in theory, these floods would be 60 centimeters higher. How much of the city that would affect? This is a map of the frequency of flooding events that we expect to see. So this is a logarithmic scale, okay? So the blues, dark blue means no change, 1 times as many flood events for, and this is under a scenario, I forget exactly what it is, half a meter. So this is actually slightly less than the best guess as to what sea level rise is going to be by the end of the century, okay? So this century, these places that have red, dark red dots are places where flood frequency is going to be 1,000 times higher than it is currently, okay? Not surprisingly, this is a lot of islands, coastal areas. And sort of the closest one to home here is actually Galveston Bay, that little light blue dot, which means flood events are going to be 10 times more likely. So now think about your flood insurance. If you live in the 100-year floodplain, that means you're going to get that 100-year flood every decade. And I've got to say, I lived in Houston for 26 years. 18 of those as someone who could really tell what was going on. I gotta say, there were a lot of 100-year floods in that quarter of a century I spent in Houston. So think about this. This is where we often see these big effects of sea level rise. Now, in theory, getting back to wetlands, when sea level rise happens, it floods these coastal systems, okay? And in forever, as long as there have been coastal wetlands, when water levels change, coastal wetlands adapt. They go with the flow, right? They live in the intertidal zone, at least the sort of systems I'm mainly speaking about. And so if that intertidal zone moves, the wetlands can move, assuming it happens at a rate over a period of time where plants can seed and move or go via vegetative growth and get into these new areas, except when there is a barrier to their migration. And I've got to say, I have a figure about this later. There are a lot of barriers these days, whether it's a levee or a city or a farm or a road. There are a lot of places where even if the wetlands can keep up and migrate inland with sea level rise, they won't if they run into a barrier, okay? So looking at how this is going to happen, there's a lot of really sophisticated 3D modeling, like SLAM models that have looked at this, and this is what I meant by a well-studied phenomenon. We know a lot about what's likely to happen just with sea level rise. So what about beyond sea level rise? What about, I'm going to speed up a little bit because it's already 6:30. What are the impacts going to be on the wetlands apart from just a rising sea level? And imagine here now you've got no barrier and these plants can migrate upward. Okay, that's an optimistic scenario, but there are lots of places where this is true. So here's Galveston Bay again, and you think about, okay, well, if you're moving into Baytown, or, that's not Baytown, but depending on whether you're in Houston proper, where it's suburbs, or if you're over in Aransas or something, Anahuac, Aransas is local here. If you're in Anahuac, you will probably get a chance for these plants to migrate, but all of these areas that are built up, like in the farmland over here, that may not necessarily be the case. Okay, so best case scenario, we're going to still have coastal wetlands. We may not have as many coastal wetlands, but they'll still exist. What are we going to see? Okay, so think about it like, envision this, right? So here's your mean sea level, and here's your tidal range, and typically within that tidal range is where you find your coastal wetland edge. And then as you approach the high water mark, you start to see upland things, and that, the high marsh, and then that grades into uplands where you don't have regular inundation of tidal water. You might still get storm water well into uplands, but this is that transition zone. And that constant grazing and lowering of tide does smooth things out. This is why a lot of these systems, especially in the Gulf Coast, are flat because of those tidal influences. And I'll point out, again, given how much elevation we have on the Texas coast, where you can go kilometers and go up about 1 meter in elevation. 60 centimeters has a pretty deep, pretty far reach. So to think about what's going to happen to these plants, let me take a step back and just remind you that we've known for ages that climate controls plants. Right? If you've ever looked at a hardiness zone map, you know this to be true. Certain plants need certain temperature ranges. Some are better at tolerating frost, some can't at all. And we can put all of the major biomes of the world in this graph where we look at temperature and precipitation. So warm is on this side, cold on this side. So warm and wet, you've got tropical rainforests. Warm and dry, you've got deserts. And of course, because of the frequency of frost, ice doesn't have the same uses to plants that liquid water does. So you can't have really cold, really wet places because too much ice. So at the most extreme end, tundra is not only really cold, it's also really dry in the sense that you may be under meters of snow or ice, but there's very little liquid water available. In the middle, you have things like temperate deciduous forests and temperate grasslands and things like that. So, and Texas kind of spans this whole area. We get some tropical seasonal forest, some temperate forest, and these temperate grasslands, and even some savanna. And these map really well to parts of the world, right? Because as you have things get colder as you get closer to the poles, and things get wetter as you're closer to the ocean. Further inland, things tend to be drier, and then there's effects of mountains and things. With altitude, you get both of those. Higher up in altitude you get drier and you get colder. And at a Texas scale, we see this similar pattern. There's sort of an east-west moisture gradient, and things are a little bit cooler in the north. And so you have this transition, the bottomland hardwood forest in East Texas, grasslands, scrublands, and then deserts in the Chihuahuan province over here. So we know this to be true. This is straightforward stuff. The same is true within coastal wetlands. There are different types of coastal wetlands based on climate, and the Gulf of Mexico is a fantastic place to study this because we have a really great natural laboratory where we have a broad precipitation gradient across the Gulf Coast, and we have a pretty significant change in temperature. This is the best map to show that, but there's enough variability in temperature across the Gulf Coast that we see mangrove forests and herbaceous salt marshes and succulents and all that good stuff. And so this is a fantastic place to study this, and it's obviously relevant to lots and lots of people. So in addition to climate, a lot of other things influence which plants grow where in coastal wetlands and whether they grow or not, including biotic factors, things like competition with other plants, facilitation from other plants, herbivore pressure, diseases, things like that. So this, for example, is showing that whether you have competition with a neighbor can be a negative thing in certain conditions, and it can be a positive thing in others, because sometimes it shields you from wind or shades you from the sun. And of course we have salinity gradients within estuaries, and things like elevation. Elevation is often the best predictor of what plants you'll see where, because it has this cascading effect of all these different abiotic factors, okay? So elevation, biotic factors, salinity, as well as climate. And we have recently learned, in some work that Mike Oslin did before I started working with him at the USGS, was that really, when we look at coastal wetlands, we see a few big overarching patterns. The first is that the severity of winter cold really governs whether or not these coastal wetlands are dominated by either grasses or graminoids, including sedges and rushes, or mangrove trees, okay? And here's 4 pictures that show exactly this. These are 4 different metrics of winter cold severity. Minimum temperature, mean annual minimum temperature, whatever. But in all of these cases, you have this threshold point where you reach this level of coldness where mangroves can't survive. Black mangroves are what we have here in South Texas, and they are the ones that are most cold tolerant. We occasionally find some reds, but they're not naturally occurring here. You do find red and white mangroves in Florida. So past this, mangroves begin to dominate. Colder than that, you have dominance by graminoids, okay? However you want to quantify that. Similarly, we see that precipitation governs the overall cover of foundation species. When I say foundation species, I mean things that are dominant across large spatial scales. They're things that are create the actual physical structure of a habitat, right? So the trees that make a forest, the grasses that make a grassland, those are the foundation species. And as well as they are the foundation of food webs, right? right? So all the different things that eat plants and eat the things that eat plants, they're largely supported by these foundation species. And there's sort of 4 foundation functional groups that we see in the Gulf Coast. In fact, in wetlands all over the world. There are mangrove trees, there are graminoids, there are succulent plants, and then there are flats, sometimes covered with algae, sometimes just mudflats. So the wetter you get, the more you see total plant cover. Okay, they're responding largely, total plant cover is responding largely to moisture. So our big question was, how are these changes in the macroclimate, temperature and precipitation specifically, that are coming with climate change, that are ultimately driving, at least in terms of temperature, driving that sea level rise by affecting all those ice sheets that we talked about before. What's that change in temperature going to do itself to these plant communities? And how are these changes in rainfall going to affect these plant communities, their structure, and their productivity? And so this was particularly timely because most of the models that are looking at what's going to happen to the Gulf of Mexico wetlands in the future focus on sea level rise, for very good reason. It's the elephant in the room. And very few of them, however, pay attention to the associated changes in temperature and precip. And so we built some models based on temperature and rainfall to try and connect climate to particular plant functional groups and community structures. And then we're using those models to make specific local and regional forecasts as to what we think is going to happen to the coastal wetlands in these areas. I'm going to skip over this for now in the interest of time. Suffice to say, we've collected the data, made the broad models, and we're working on these fine scale things where we use a special kind of math called structural equation modeling, but that's still in process. So here's the study system. It's the Gulf of Mexico. We looked at 10 estuaries going clockwise, like all the way around the Horn. So from South Texas all the way to the Everglades, and 5 in Texas. And you can sort of see the ones in Louisiana, Mississippi, Alabama, those are your coldest and your wettest sites. Going westward, Galveston Bay is a little bit colder, a little bit warmer and a little bit drier, and that pattern continues as you go south in Texas. San Antonio Bay, drier and hotter still. Mission Aransas, which is sort of the current fulcrum of mangrove dominance. And then you get into Baffin Bay and the Laguna Madre, where things are most very dry and very wet. Definitely the driest sites we saw. Florida is interesting because you get a lot warmer as you go through Florida, but it stays wet. So we have separate axes of these 2 factors that we can then analyze and get out. So within each of these estuaries, we position this series of transects because we know there's a lot of variability within an entire estuary in terms of salinity and things like that, as well as tidal range. And within each of these transects, we followed an elevation gradient, and we ran a transect. So this is that one over there, and not technically Baffin Bay. And this gave us a view of all the different plants that were there across these different gradients of salinity as well as climate. Okay. And so overall, we studied 10 estuaries. We did 70 transects and measured over 1,000 plots. We looked at soil physicochemistry, we measured elevation with a real-time kinematic GPS, and we, of course, surveyed plant community structure. So, again, we want to focus on these 4 functional groups, because even when the species differ, you might get different grasses or sedges or rushes, you always see these same 4 functional groups. Mangrove trees, graminoids, succulents, and then unvegetated areas that may or may not have algae mats associated with it. And yeah, so these 2 are the wetter areas, and then drier and drier still. So here's our brief summary of what these different functional groups are. So across the Gulf of Mexico in these 10 estuaries we surveyed. Blue are the graminoids, red are the mangroves, gray are the succulents, and yellow is unvegetated. Think yellow like sand. And I'll kind of stick to these colors, so try and internalize that here. And so lower Laguna Madre, this isn't going to be a surprise to anybody here. And this is sort of looking at along an elevation gradient. That's what the 4 different stacked bars are. So a good amount of mangrove dominance, quite a few succulents, fair bit of unvegetated areas, and then a scattering of grass. Baffin Bay is even saltier, so you get fewer mangroves, more unvegetated areas. Aransas is a good mix of grasses and succulents, as well as, grasses, succulents, and mangroves. And then as you start going clockwise around, you start to lose mangroves because you're getting colder, and you start to gain grasses. And you still have a lot of succulents in eastern Texas because it's not super rainy there. By the time you get to Louisiana, Mississippi, Alabama, it's entirely a grass-dominated world until you get into Florida, where it's still warm, but it's very wet, and then you're dominated by mangroves. And this is true in most of Florida bays, at least sort of south of the Panhandle, except when you get into the Everglades and you start getting some interesting grass systems as well, graminoid dominant systems. So, each of these dots is one of these estuaries. And we're looking broad scale here. We can build these models that say, all right, here is, both of these are temperature. As you increase in temperature, you can fit a best fit line to find out what the rate of increase in mangroves is. As you go up in temperature, these are getting less cold in terms of winter severity. And you get a decrease in graminoids at the same time. They're giving way to the mangroves. And so if you look at precipitation, we see a similar pattern. Grasses and mangroves like the wettest areas, and we've modeled them together here. So areas dominated by grasses or mangroves go up quickly as precipitation increases. Succulents never become super dominant, but they definitely hit their peak at about 1,000 millimeters of rainfall a year, a meter of rain. And unvegetated goes up quickly as you get below 1,000 millimeters and things get drier and drier. We can also model height this way, and this is no surprise. You start to get really tall stuff when you get warmer because it's going into mangroves. And even proportionally. Now this is an absolute change. This is a proportional change. And we see a similar increase with precipitation. And so what this means is that from 0.2 to 1, that's a 5-fold increase in height. And you see this if you look at sort of the average height of mangroves in South Texas. They might be 2 or 3 meters tall, whereas the same species of mangrove, black mangroves in Florida, could easily be 10 or 15 meters tall. All right? And it's that change in rainfall that's doing that. All right, so from this, there are equations for these lines, as you hopefully learned in school. And these are those equations. So don't worry about the numbers here, but know that this is the equation for this line. This is the one for the red mangrove line. Here's the one for this based on moisture. This is the one for the succulent relating to moisture, yellow for unvegetated and moisture. And we combined these by putting these equations together to look at both how much graminoid dominance we would expect and how much mangrove dominance we would expect based on not only precipitation, but based on temperature as well. We didn't do a combined model for succulents and unvegetated because they were really only responding to precipitation, not to temperature. They don't really care how cold it is. Succulents do well in the cold also, and as well as in the warm. They're responding mainly to rainfall. So we made these equations. We combined them here, these equations that are modeling our observed patterns, and we did the math to solve these equations for all the relevant range of temperature and rainfall that we might expect to see in the Gulf of Mexico. And then I did some coding in R to create these 3D maps that predict basically what we expect to see along this range of temperature and rainfall. And that's what this is. So this is actually pretty intuitive, I like to think. So air temperature along the x-axis, precipitation along the y-axis. And so graminoids, they do best where it's cold and wet. Mangroves do best where it's warm and wet. And again, succulents and unvegetated areas don't respond to temperature, which is why they're just flat lines. They're responding to rainfall. And again, succulents doing best at about 1,000, and unvegetated areas going up quickly as you get below about 1,000 millimeters of rainfall. You can put all these into this same one big thing, and you can actually take its spot, point at it, and say, okay, in a place that has a minimum air temperature of -10 and 1,000 millimeters of rainfall, we're right in the middle. We would expect about an even amount of grasses as well as mangroves. We'd see quite a few succulents and not much unvegetated land. And this maps fabulously to what we actually see in these areas, right? So that's your first check on whether these models are real and making sense. What we did here is we drew rectangles based really simply on the range of conditions we saw in the last 30 years in these different areas. These boxes are different sizes because we were more interested in the climate in these areas. So we put boxes around places that had distinctive sort of temperature and rainfall regimes, right? So all of Louisiana, Mississippi, Alabama, and Northwest Florida were pretty similar in terms of their rainfall and temperatures. And then as you get into Texas, you're getting drier and warmer, drier still, warmer still, drier still, warmer still, and then Central Florida, warm but wet, okay, and South Florida more so. And so if you look at what you find in South Florida, and you map it, and you look at where the box was drawn based on its climate, you say, hey, that's exactly right. In South Florida, we mainly see mangroves, we see very few grasses, and we see a few succulents. In Central Florida, it's a lot more variable, right? And our Central Florida site was Tampa Bay, but you definitely see areas where there's a fair bit of grass cover as well. And then you get into places like Mission Aransas, or the, not Aransas, but Mission Aransas, Naturalist Research Reserve near, not too far from Corpus Christi. And that's Central Texas, right? And this is exactly what we see out there. That is the crossroads of mangroves in Texas. You have a good mix of mangroves versus grasses and a lot of succulents. Here in South Texas, we get a little bit of grass, right? It's represented by that lowest band of grasses, mostly mangroves, but a lot of succulents and a lot of unvegetated areas. This is what we see. So these models are talking some sense, okay? And so this means that we could very easily make projections just by shifting these what we call climate envelopes just by moving them along. If we want to look at what might be in these zones, if things were 2 degrees warmer, just push everything over 2 degrees. And what then is contained within that box is a pretty good, and and with the program I wrote, we can easily calculate exactly what you think those abundances of different plant communities can be. All right, so if we see things getting warmer, we see a shift. And what does that mean? Largely a shift where you lose grasses and you gain mangroves. Pretty straightforward. All right, and similarly with height, where you're warm enough to start getting real mangroves, you get quite a big increase in plant height as well. And if you get warmer and wetter, you're moving away from those unvegetated patterns, and you're basically just getting more cover, right? And taller things as well. If you get drier, you're getting more succulents, you're getting less total veg, okay? Straightforward, really pretty intuitive stuff. Okay, so those were pretty conservative projections. Those were 2-degree increases in temperature, and no one predicts decrease in temperature. There's no models that predict that. What about larger changes in climate, including rainfall? We didn't really even touch on rainfall. 4-degree increase in climate, and we see that Northeast Texas, that's Galveston Bay, is basically is beyond where Corpus Christi is today. So my kids are 7, 5, and 2, and, she just turned 6 last week. And in their lifetime, when we go visit Texas, and I take them fishing where I learned to fish in Galveston Bay, it's going to look like a world of mangroves. It's not going to be the salt marsh that it is today. So these are very profound changes. And it's because of that threshold effect. We're already on the cusp of that shift from grass to mangrove dominance. South Texas, though, and again, I want to focus on local systems here, we're already in that warm world. So what are we expecting to see? If we get an increase in precipitation, we would see more succulents, but we'd still probably see the same relative proportion of mangroves. But what we're probably more likely to see is a decrease in precipitation. In this case, we're going to see a loss in vegetation. Fewer mangroves, fewer succulents, more algae mats, more mudflats. And that's a big deal. Possibly 20% less. And if you think about 20% less of foundation plant species, fewer plants, smaller plants, more areas that are unvegetated, when that plant or those systems are the foundation of entire ecosystems, that's going to be 20% fewer things that eat plants. And that affects birds, that affects fish, that affects reptiles, that affects people. So We can also map biomass related to production, but it largely follows the height thing, so I don't need to spend much time here. Here are some specific calculations. In the interest of time, I'm not going to go into this, because I'm going to talk about lower libido madre specifically. I do want to point out that this is not unique to South Texas. This is, and I have about 10 minutes left, so I'm going to speed up even more. This is a global phenomenon. All these areas around the world are either, if they're in blue, along that rainfall gradient, where you're going to see big changes in these coastal wetlands based on rainfall. If they're in red, you're going to see big changes based on temperature, shifts from marsh to mangrove. And if it's purple, you're going to see both, and that includes the Texas coast. So we're seeing these big changes, and that's why one of the main reasons I was super keen to come and work here in South Texas and get a job in the valley. So this is a global phenomenon. The species are different, but the functional groups are the same. Mangroves, succulents, graminoids, and flats. Every coastal wetland in the world. All right, so how is this going to affect me? Why should I care about this? Who cares if there's mangroves instead of grasses? Or I lose some succulents? First one's already ignored. All right, so big questions about us locally. How's this going to affect South Texas? Big questions are, what's actually most likely going to change here in South Texas? I've already touched on that a little bit, but we'll go into it a bit deeper. And how is this, how is the climate change? I didn't talk too much about projected climate for South Texas. So what is actually going to change in our climate? How is this going to affect our wetlands? And what's that going to mean for us? So Texas is kind of unique. Each of these maps of Texas with these goofy codes is a different climate model. And this isn't the kind of model that gets run on my computer in my office. This is done by a government supercomputer. I think of this, and there are actually like 65 of these in the world, but these 20 are considered to be the most reliable. So I think 6 of them are from the US, 1's from Canada, 3 are from China, 4 from Europe. I don't remember where the other ones are. But these are government scale efforts to model climate and predict what's going to happen. And you might see that if you look at the 20 model mean for Texas, no change in climate. I'll note that this is RCP 4.5, so this is a pretty optimistic scenario. But that's misleading because these models predict different stuff. That's just the average, okay? About half predict it getting wetter, about half predict it getting a little bit drier. So we don't really know. If we look at one of the more pessimistic scenarios, we see that there's, and the colors are not super great, so I apologize for that. Texas is expected to get drier, okay? Some think a lot drier. Others, not so much. Maybe even a few where we might get some increases. Which of these models is right? Nobody knows. Some of these have been better in the past at predicting things. But generally, looking at ensemble models, those average models, don't generally lead us far astray. Climate models have been around for a long enough time that we can measure predictions over decades. And they are pretty good. They are very reliable models. And very important thing to note, no matter what happens with rainfall in Texas, we're likely going to lose freshwater availability. So effectively less rainfall. And this is because it's getting warmer. Warmer air means more evaporation, and in some areas more strongly and more importantly, more transpiration. So warmer weather means plants lose more water through their stomata, which means more water leaving the soil, leaving wetlands, leaving estuaries, going into the atmosphere. There's also growing municipal demand, right? The Rio Grande Valley is one of the fastest growing areas in the US. That means more people running sinks and showers and toilets. That has to come from somewhere. This one, we're not really sure about either. We don't know if there's growing agricultural demand, but we use a lot of our water for irrigation. Currently more for irrigation in South Texas than for municipal demand. And one of the predictions that all the models agree on of climate change, even if they can't agree on whether we're going to get more or less water, it's that that rain is going to come in fewer larger storm events. So imagine whether you have this regular light rain versus a couple of hurricanes. That water doesn't get absorbed as well. That runs off more. So you're going to have less water being absorbed by terrestrial soils and plants, and it's also going to mean more erosion. That's a whole other beast. And one bright side to this, it may mean more water getting to the Lagoon Madre. So if we get more stormwater and general runoff, this could get to the Laguna Madre, but that's already causing problems. The Laguna Madre historically was a hypersaline system. We've opened up enough passes from the Gulf into Laguna Madre now that the salinity's been going down, and it's losing that hypersaline status. And there are winners and losers whenever those things change. Some fish like that, others don't. But it has been going down. This could further reduce salinity, but it might also mean some of these coastal plants get a little bit of water that they might seriously need. And fewer rainfall events also mean more drought stress between those rainfall events. So however you want to slice it, we're going to lose water availability in South Texas, which means this is the most likely scenario. This decrease in rainfall, or I should just say a decrease in freshwater availability, which means we're going to lose plant material. Less, smaller plants, fewer plants, more areas without plants. Maybe 20%. So a better way, I think, to illustrate this is with an actual illustration, which I try to do. So this is Grand Bay. It's not the best example, but it is a good example of a wet system where you get a lot of dominance by grasses. And if this was Florida, the grasses would just be mangroves. And then you get an upland area. They have salt pans out there too, which are like large swaths of Laguna Madre. And then you get a different set of grasses grading into trees, slash pine forest in Mississippi. In Mission Aransas, Texas Coastal Bend, you have this cool zonation where you have Spartina in the water, and then at the fringe, you start to see mangrove dominance, and that grades into succulent dominance. Then it'll occasionally have mud flats or algae mats, and then you get into upland veg. Sometimes trees, a lot of times just different grasslands. Here in Lower Laguna Madre, we have a lot less Spartina. We have black mangroves, but it's a narrower band typically, and they're typically smaller because we're more water limited. And then we have a smaller band of succulents on the landward side of those mangroves. We often have algae mats, and then areas where there's no algae even, it's too salty even for algae, before we get into this upland edge, which is often succulent dominated. So here's, and this is a good example of what happens as you get drier, okay? So this is my title slide photo, and that's why I picked it. This is a fabulous summary of these systems in South Texas. You've got your mangroves along the water, and there's some succulents behind it. That's Batis maritima. Then you've got algae mats, a bit of mud flat without algae, and then you get into the uplands, okay? And succulents at the upland into taller grasses, and eventually your taller trees, like in this case it's yuccas, okay? So, more qualitatively, what do we think might happen in Laguna Madre this century if we see these changes in climate? Well, if I had to guess, and it's a guess, but it's an educated guess. I gotta say, I think about this a lot, and we've done a lot of math and studying on this. If the same kind of patterns hold true, a few things happen as things get drier. You tend to have a pinch of that intertidal vegetation, and you tend to have an expansion of those unvegetated areas. And this, I must say, if this happens, this could be that 20% loss in vegetation that those models predicted. And it's possible these upland things would get pushed back a little bit. The pinch might be too much for smooth cordgrass Spartina alterniflora. We may lose that entirely. It's already pretty uncommon. But it typically survives by being able to tolerate lower elevations than mangrove trees do. So it might still stick around. But qualitatively, this I think may be where we're headed, okay? So I'm essentially out of time, but I haven't yet been stopped. Can I have 5 more minutes? 2 minutes.
Go for it.
Okay, I'll make this quick. I think you guys probably already know this part. So why does this matter to us? These are some big changes ecologically, but are these really going to affect you and me in my everyday life? And the answer to that is, if you like to spend your time on the coast, it's going to impact you in a massive way. And then if you don't, it's still going to impact you in a big way. And if I can impress upon you no other lesson, it's that the types and the amounts of plants that you find in a system, which kinds of plants and how many of them there are, that governs the types and the amounts of ecosystem services that land provides. And you guys have know what ecosystem services are, probably a common theme in this program. And so and I'll talk about these anyway, show you some examples. So when plant community structure changes, you get a change in the amounts of and types of plants, and that means a change in the amounts of the goods and services that these wetlands can provide. So coastal wetlands are the poster child for ecosystem services. They help us with storm protection, larger areas of coastal veg, taller veg, denser veg, more rigid veg, all helps stop storms. Storm surge, wave action, wind action. Those plant roots reduce erosion. Coastal wetlands are one of the best things around for reducing waste, absorbing all those nasties that come through the watershed, assimilating them in plants, locking them into soils, taking them out of the water we drink. They're really fabulous, especially for nutrient pollution like excess nitrogen, phosphorus. Wildlife habitat, of course, support of our commercial and recreational fisheries. They also just help hold water, okay, including fresh water. And recreation and ecotourism is huge here in the valley. I don't need to tell you guys this, but the amount of people who come here to fish or watch birds, those coastal wetlands are super important for these things, right? And something that often doesn't get played up as much is carbon storage. They're 3 times better than tropical rainforests at storing carbon. And the reason is, it's all below ground. A salt marsh only has a tiny bit of living biomass, but all those rhizomes below ground are what really stores the carbon. And the reason is, it's underwater, so it's anoxic, so it can't decompose. It's also salty, which slows decomposition. And that's all you really need to start accumulating a lot of peat below ground. So if you look at all the different things that wetlands can do, these are ecosystem services, provisioning services, food and water, regulating air quality, taking away waste, preventing erosion, cycling nutrients, and then habitat services. All of these have been valued by, there's a whole line of ecological economics that looks at this. And if you look at what a square kilometer of wetlands do, just by being wetlands, not developed, not doing anything else, just letting nature do its thing, the dollar value to us is almost $5 million per square kilometer. That's a lot, and that's one reason why we spend billions and billions of dollars on wetland conservation and restoration. It's a good investment. And to compare this, the average tropical rainforest is only about $500,000 per square kilometer. 10 times more valuable in human terms than tropical rainforest. So that's the end. And thank you for giving me this time. I'll just kind of close with this reminder. We're going to see warming of 2 to 4 degrees Celsius. This is going to be happening in partnership with a 40 to 60 centimeter rise in sea level. We're going to see big change in plant community structure as a result in those surviving wetlands. They're still going to be wetlands, but what they are is going to be governed by climate, temperature, and rainfall. And for most of the U.S. Gulf Coast, there's going to be a big transition from salt marsh to mangrove forest. And this isn't all doom and gloom. Mangrove forests are fabulous, productive systems, but there are going to be winners and losers. And we as humans aren't so great at change, right? So if we change the fisheries, it's going to affect navigation. It's going to be some rough waters ahead. And I'll point out that we also have major areas facing eutrophication from things like human sewage, runoff, ag runoff. That's a whole different set of problems that has a whole different set of consequences, but it's happening in a big way, also leading to dead zones. In South Texas in particular, we're not really facing that marsh to mangrove conversion because we're already warm. What we're mainly seeing is a conversion of mangroves to succulents and a loss of veg. So we're getting so dry that we're going to just start losing vegetation. And that's going to result in a significant loss in ecosystem services that we as people benefit from. And this is getting complicated by competing demands on our water. So I don't have time to tell you about this. I didn't really realistically expect I would. But I'm going to zoom forward to my contact information. There we go. So if you have any questions, please feel free to reach out. I'm happy to talk. Thank you very much. I don't think I have time for questions, but
Yeah, go ahead.
yeah.
Hi. I just wanted to say, for your modeling and stuff, I was curious about the certain level of assumptions and limitations that your models are.
Every model has
I know,
assumptions and
but
limitations.
some like general ones that specifically those models that you developed with your research.
So modeling should be as simple as it can be to get things across and not more complicated. Because the more complicated you make them, the more idiosyncrasies you see. The big assumptions we made were that we were mapping it at a course scale, at a sort of estuary scale, okay? So if certain parts of estuaries behave away from the norm, like if some are less, if there are unusual sources of water or unusual protections from sea level rise or things like that, then we wouldn't necessarily expect that the same change that we're predicting to happen in all places. But by sort of zooming out, we're sort of talking like generally this whole estuary system is going to lose some mangroves, gain some grasses, whatever. So that's kind of the biggest assumption, is that they're all going to behave the same way. And we don't, I would say this, increases in rainfall don't have the same effect everywhere along the rainfall gradient, but we do account for that in our actual models, right? So if you're in an area where you're already wet or dry, then getting warmer isn't going to affect you that much, right? So by incorporating these nonlinear models, we tried to not make too many assumptions about consistent change. In fact, we specifically expect that change is going to be nonlinear. So, I mean, is there anything in particular you thought might be glossed over here? I'm just curious.
No, I mean, I don't want to take up people's time, but I was just...
Let's chat about it some other time. You know how to get
Yeah.
All right. Yes, sir.
I know it's a small scale, but what goes on at the birding center next to it? There's a treatment plant, and it's creating a sort of a...
It's a source for fresh water, and so that's why you get gators there. That's the only
I'm
reason
just
you get
curious
gators
what's kind of going on.
there. Yeah, so there is freshwater effluent from the treatment plant that is, and I'm not sure how treated it is, but it's whenever water comes out of a treatment plant, it's enriched in nitrogen and phosphorus because it's came from sewer water essentially, and so it makes that area fresher and more fertile. And fertility is not always great, right? So that's one reason why you have so much cattail over there in that one particular area, because cattail is a weedy native, and it responds to that pulse in nutrients pretty rapidly. I'm surprised I don't see more algae in that area, because that's usually the first thing to bloom, but the plants there are so productive, and you get so many herbivorous things out there that I think they're helping keep the water relatively clear.
It seems fairly healthy.
But it is unusually
Let's
wet
get
there.
down there.
In fact, I take my plant morphology and my marine botany classes to that site because it's a great way to get a fresh to salt gradient along the coast in, 80 meters. It's fabulous. Yeah.
Right.
Great question. Yeah.
I was wondering what you expect to happen to the Rio Grande River.
So river systems are decidedly a whole other set of math and expertise. Given how much water we're already withdrawing, and given I'd have to sort of look, and the data's out there. People look at this. I'm not one of those people. But I'd have to do my homework to tell you the answer to that. But if we get more rainfall in its watershed, you could see more water coming through. But from what I understand about most of the projected climate change for the western U.S., that's not likely to happen. So we're already seeing major low water levels in the Rio Grande all the time. There are parts of the Rio Grande that are dry every year, and it's probably going to get worse because we are likely to see less rainfall, more evaporation, and like here in the valley,
We're at the end of the trail.
more extraction from humans and for irrigation and municipal use. And so a fun example of this, interesting example of this is the Arroyo Colorado watershed, which is essentially a new river system because of all the water we take out of the Rio Grande over the levee into Brownsville, McAllen, etc., and then drain to the Gulf Coast through a series of resacas and connecting tributaries. And so the Arroyo Colorado watershed is our extraction from the Rio Grande, essentially. It used to be far smaller and lower volume. So that sort of thing is probably going to happen all over and exacerbate the effects we're already seeing on the Rio Grande. But again, that's not my particular area of
Is there
expertise.
ground, we have a lot of groundwater.
We do. And so when you extract groundwater or surface water, what happens with the hydraulic pressure from the sea is that you get more seawater seeping in, which means more areas right now that are borderline too brackish to drink are likely to be too salty. So some of our groundwater sources are going to no longer be viable for drinking water. That's one reason why I'm doing some aquaponics work where we're trying to cultivate plants in brackish water instead of fresh water, because that would make for some very productive use of those brackish well waters. But that's a big issue.
Well,
Lots of people are
they're
concerned about.
looking at spending millions on the water treatment. So.
The desalinization plants in like Brownsville and places.
No, to fix the ones we already have that's coming from the
Yeah,
water.
and
So-
it's going to be more of the same. The more our current sources become limited and our sources become more saline, we're going to have to purify more water to meet demand, and demand's also just going to go up. So I think millions is going to turn into tens of millions.
Would you
sooner rather
recommend
than later.
a desal or a groundwater?
That's an engineer question. I mean, it's tricky. It has to do with the energy requirements for what, and cost, of course. You know, because nothing's going to be sustainable ecologically. Or I should say this: I'm big on sustainability. I even hold a special sustainability position at the university. But we can't just consider ecological sustainability. We have to consider social sustainability and economic sustainability. Because even if the nature likes it, if it makes people poor, it's not likely to last. So we have to put all those three things together as best we can. So systems that are sustainable, don't use too much energy, and are actually cost effective. If you know the answer, you have a wealthy future. So,
Thank you.
all right, I've probably taken way too much time.
Fine.
Okay, I thought somebody else was about to.
7:20, 7:30.
Oh, great, I have time for more questions then. Okay, good.
Absolutely.
I'm happy to field as many as you guys can throw. Or not. Yeah, go ahead.
I always have a lot of questions.
Perfect.
Is there like a dead zone starting to form on the mouth of the arroyo?
Yes.
Didn't hear your question.
She asked if there is a dead zone forming at the mouth of the Arroyo, Colorado. Yes, but it's not as exaggerated as obviously the Mississippi's dead zone is. Right? The Mississippi River dead zone is the size of New Jersey, the state of New Jersey, not the city of New Jersey, the state. It is massive. And as you might expect, it's all of the U.S. Midwest breadbasket, all the corn farming that goes on in the Midwest, all that fertilizer runs into the Mississippi watershed and it gets spit out into the Gulf, and you have this massive dead zone. So the mechanism for that is fertilizer comes in. The things that can take advantage of it first are the simplest, fastest growing organisms, which are algae and cyanobacteria. And so you get a bloom in algae, which means your clear water turns pea green, and then when the water turns green, it becomes opaque. So sunlight can't reach the bottom, which means your benthic plants die because they don't have enough light, so they're not oxygenating the water. Those photosynthetic algae do produce oxygen, but they also die, and when they die, they sink to the bottom, where bacteria and fungus break them down, decomposition. Decomposition requires oxygen. So as they decompose things, they suck oxygen out of the water column, and the water literally becomes anoxic. And then everything that didn't die from the shading dies from being anoxic. And you'll have massive fish kills every year, all the time, regularly. It's affecting migration patterns of everything from sardines to tuna to whales and dolphins, because they know there are no fish in there to consume. So they avoid the dead zone literally like the plague, and for good reason. Even marine mammals that breathe atmospheric air don't go in there because there's no fish to eat in there. So that is happening at the Arroyo, Colorado, but not at such an extreme level. There's absolutely eutrophication there. And really in fact, I have a colleague, you guys might know Hudson Dayo. Mm-hmm. Some of his students are working on outflows in parts of the Luna Madre related to the Arroyo, Colorado watershed. And one of the impacts we're seeing currently is an effect on the seagrasses. So it's triggering, you think, oh great, fertilizer, it's seagrass. But the same thing, because it's the algae that are taking advantage of it first. And seagrasses have like an incredible, as the ecologist, I was surprised how many different things live on a blade of seagrass. Like the amount of like microcorals and algae and things is incredible. Like literally hundreds of species on a single blade of seagrass. And those algae respond first. So they grow, and they're epiphytic. They grow over the top of the seagrass blade, cover it with algae. The seagrass then doesn't get any light, so then the seagrass dies. So fertilizing seagrass kills it because it triggers the algae that live on seagrasses to proliferate. So that's happening already. Not the same kind of dead zone because of anoxia, but definitely affecting our coastal ecosystems. Great question.
Can you explain a little bit more about how it would, losing the hypersalinity of the Laguna
Right.
will affect us?
So every plant animal in the ocean and in the coast and in the laguna has a preferred ecological niche, right? Some like it more saline, some like it less saline, some like it shallower and wetter and whatever. And what we've kind of seen for the long time, like looking historically, it was more hypersaline sets of species. Now, and if you look back at the record, a lot of times when there would be a hurricane and there would be like big storm surge from the Gulf, that pulse, because the water in the Laguna Madre would often reach like 50 or 60 parts per thousand, which is double seawater. So when you get a big storm surge event and it pushes a bunch of seawater into the Laguna Madre of 32 parts per thousand seawater, it causes the salinity in the Madre to go down a lot. And that would often be followed with a year or two of really great fishing. But the regular exchange, like that was sort of like, here's a feast year after a sort of decade of like good fishing, but a really fantastic year after fishing, the bright side of those hurricanes. With the regular exchange, it's really just becoming more like other estuaries in Texas. So it's becoming more like Aransas Bay or Galveston Bay. And it's affecting the seagrasses. So there's been a major shift from Thalassia, it'll come to me. The thin one, the needle shoalgrass to Thalassia turtle grass. And that's because turtle grass has a preference for lower salinity. So it's affecting the seagrasses, which affects all the things that eat seagrass. Thalassia is still a great thing. It's affecting the algae that grow on the seagrasses, and it's affecting the fish that live there. But again, like that's not necessarily a bad thing, it's just a different thing. And we are losing a lot of the diversity that we had here because of that unique situation where we would have more fluctuation between high and low salinity. When you have systems like that that are variable, you tend to have more diversity because you have stuff that likes one condition, stuff that likes the other condition, and things that like in between, rather than just one where you lose kind of half of those things. So we still have great fisheries, we still have highly productive system, but we do have less diversity and we are seeing big changes in what's there. And it's not really clear what the future holds for salinity in the Laguna Madre. So, all right. Thank you all very much.
Thank you.